Math 2414, Calculus 2, Calculus 1 Review, Derivative Rules Part 4. In the previous video we derived well, we didn't derive all of them, but we reviewed the derivatives of all 6 trig functions: sine, cosine, tangent, cotangent, secant, and cosecant, all of which you need to have memorized. In this video we're going to derive some derivative rules for inverse trig functions. And if you notice, I've only got 3 listed so far. But before we jump into them, 2 comments. Number 1, the notation for inverse trig functions is not consistent. If you'll notice, I'm using the arc notation, arc sine of x. But that just means sine inverse of x. I personally prefer, at least in calculus, to use the arc sine notation instead of sine inverse of x. Because in calculus, we've got enough things living up where the exponent normally does. An exponent, a prime meaning derivative, and algebraically speaking, you can also have a -1 up there meaning an inverse function. But a -1 as a power means reciprocal. So this notation is prone to misinterpretation if you're not careful. However, arc sine is fairly uninterpretable. It means inverse sine of. I'm not going to go into the history of why it's called arc sine, but just a quick comment. It's asking the question, whose arc on a circle has a sine of a certain value if you think about trig from a circle perspective instead of a triangle perspective. Now, it won't bother me if you use the -1 notation for an inverse trig function. However, I will consistently use the arc notation. Second comment, you'll notice that I've only got 3 inverse trig functions instead of 6. Arc sine, arc tangent, and arc secant. The reason is these are the most useful ones. There is arc cosine, arc cotangent, and arc cosecant, which I will add to this list in a moment. But once you know these 3, the other 3 are real easy. You just stick negatives on them. All right, so let's start with arc sine of x. Now I can just give you the derivative, but if you've been watching the previous videos, you know that I don't just want to throw things up there and say, know them. I want to show you where some of them come from for 2 reasons. Number 1, to make your brain work better. And number 2, if you forget a rule, you might be able to reinvent it. So how do we find the derivative of arc sine of x? Well, the same way we've done other derivatives, we take what we don't know and connect it to something that we do know. So let's take this function, f of x equals arc sine of x. And just to remove this f of x for a moment, let's replace it with y. Oh, and by the way, before we get too in-depth into this, from a trig perspective, inverse trig functions have specific domain and range limitations. I'm not going to review them all right now. If you're curious, I'll hook you up with some review content. All right. So let's say that we have y equals arc sine of x, and we want to figure out what y prime is equal to. We can connect this to something we already know, which is the derivative of sine. The only problem is we don't have sine, we have arc sine. So why don't we take the sine of both sides? Sine of y is equal to the sine of arc sine of x. Now we do have to assume that this x is in a certain interval of values, specifically between -1 and 1, but assuming that it is, when a function is composed with its inverse function, they cancel each other. That's what inverse functions do. One function does something, the inverse comes in and undoes it and gives you back what you started with. In other words, the sine and the arc sine cancel, and we're left with sine of y is equal to x. Well, that's great because I know how to take the derivative of sine of y. But here's where we have to be a little bit careful. We're taking derivatives with respect to x, and this is not an x. We have to use implicit differentiation. If you've forgotten what implicit differentiation is, please go back to Calculus 1 and review it. But let's take the derivative over here with respect to x. I'm just going to put ddx to indicate I am taking derivatives with respect to x. The right side is easy. The derivative of x is 1. It's just a very specific instance of the power rule, combined with the fact that anything to the 0 power is 1. Any non-zero number to the 0 power is 1. But how do we take the derivative of the left side? Well, we know the derivative of sine. Derivative of sine is cosine. And implicit differentiation basically says because this is not the variable with which we're taking the derivative with respect to, that was an awkward sentence, we have to implement the chain rule, and even though I haven't reviewed the chain rule, let's assume that we've had, and we got to multiply times the derivative of the inside. The derivative of y is y prime, or more specifically dy dx, if you will. And that's what we want to know. What is dy dx, which is just another name for f prime of x here. Well, we've got an equation involving dy dx, and now we just have to solve for it by dividing both sides by cosine. So dy dx is equal to 1 over cosine of x. Now, I could call that secant of x, 1 over cosine of y. Now, I could call that secant of y, but that's not my biggest problem. My biggest problem is I'm trying to find this derivative as a function of x, and it is currently a function of y. So how can I change this to just x's? Well, what do I know about y? It's equal to arc sine of x. So we could say 1 over cosine of arc sine of x, which is not wrong, but it's just ugly. From a trigonometric perspective, this can be rewritten without any trig functions at all. How? Well, go back up to where y came from. Y is arc sine of x, or sine of y is equal to x. I can draw a picture of this. If I say sine of y is equal to x, y is an angle, we'll put it here, and sine is opposite over hypotenuse. So how would I draw this picture so opposite over hypotenuse would equal to x? Put a 1 on the hypotenuse and an x on the opposite side. This is a picture of sine of y is equal to x. It's equivalently a picture of y equals arc sine of x. Now why do I need to know that? Because I want to know what cosine of arc sine of x is, and in fact I'm going to go back down here and take it back a notch. I was debating writing that line in the first place, but let's go back over here for a second. In order to get rid of this cosine of y, I need a picture that tells me how to find cosine of y, and here it is. Almost. What's the direct definition of cosine? Adjacent over hypotenuse. Do I know the adjacent side? I do not. I'm going to put ADJ just for adjacent. But can I find the adjacent side in terms of x? I can with the little Pythagorean Theorem. Adjacent side squared plus x squared is equal to 1 squared. Well, 1 squared is 1. And if I solve this for the adjacent side without dragging through the algebra, it's going to be the square root of 1 minus x squared. Which means I now know what the cosine of y is. The cosine of y is this over 1. So the cosine of y is this over 1, which is just this. And we have the derivative of arc sine of x in terms of x. Now that was a lot to go through because it did involve knowing a lot of trigonometry, how to trick out a triangle to satisfy a certain trig equation, and a little bit of just a little bit of calculus here. But the net result is, and here comes the rule, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. All right. I'm going to derive arc tangent also because I really think witnessing where some of these rules comes from makes you a better math person and a better thinker in general. Even though we're just reviewing these rules, like I said, I think it's time well spent deriving some of them. I challenge you to try to derive the rule for arctangent using the same process that I just used. If you're up for the challenge, pause the video and give it a go. And you're always welcome to pause the video and try a problem before I complete it. But if we were to do the one for arctangent, we would start the same way by saying y equals arctangent of x. And then taking the tangent of both sides to get tangent of y is equal to x. Remember, the reason we take the trig function of both sides is to get the trig function that we know about into the equation. And now if we take the derivative with respect to x, the derivative of tangent is secant squared. The argument there is y, but we have to use implicit differentiation, which is basically the chain rule, and say times the derivative of the inside. With respect to x, the derivative of the inside is dy dx. On the right side, the derivative of x is just 1. If we solve for dy dx, we get dy dx equals 1 over secant squared y. And whether or not we should write that as cosine squared y may not be evident until we get out a triangle that matches this and use it to evaluate secant squared of y. So let's draw a triangle for this equation. Not sure what happened there. If I say tangent of y is equal to x, then y is an angle. So let's put an angle here. Tangent is opposite over adjacent. How would I label this triangle so that opposite over adjacent equals x? Put an x on the opposite and 1 on the adjacent. I'm going to need to figure out secant, which is, you know what, let's just go ahead and call this cosine. And the only reason I'm doing that is because cosine is in the goofy word SOHCAHTOA. Secant is a reciprocal of cosine, and most of us think in terms of sine, cosine, and tangent anyway. But if I want to figure out cosine on this triangle, I need to know the hypotenuse. So if we do the hypotenuse in the Pythagorean Theorem, we get 1 squared plus x squared equals the hypotenuse squared. So if we square root both sides, we get the square root of 1 plus x squared equals the hypotenuse. Do not distribute the square root across the plus. That is always bad. You cannot distribute square roots across pluses. So that's what the hypotenuse is. And as a consequence, oops, I knew this was going to happen. You may be familiar with the 3-dot triangle. It's a symbol for the word therefore. It's very common in math. It means we're about to draw a conclusion. Therefore, cosine of y is adjacent over hypotenuse, so 1 over the square root of 1 plus x squared. But our derivative is the square of cosine, and if we square both sides, we get 1 over 1 plus x squared, and there's our derivative of arctangent. Most books will write it as 1 over x squared plus 1, but since addition is commutative, it doesn't really matter. So I hope you appreciate the derivation of the derivative of arctangent. It's the last derivation I'm going to do in this video. What is the derivative of arcsecant? The derivative of arcsecant is 1 over x times the square root of x squared minus 1. Let me check something real quick, because some books are a little persnickety about something in particular. Oh wait, I don't have that part with me. My computer's signed out. I hate wasting your time while I'm doing things like this, but I'll just mention it. There are some situations where you need an absolute value around this x, but I'm not going to hold you accountable for that for now. If and when I remember it, I'll look into it later, and if I feel it's necessary, I'll go into details. But for our purposes, the derivative of arcsecant is 1 over x times the square root of x squared minus 1. Not going to derive it. So what about the others? 20, 21, and 22. If f of x equals arc cosine of x. I always only put one c there. Then the derivative of f of x is equal to. Number 21, if f of x equals arc cotangent of x. Then the derivative of f of x is equal to. And number 22, if f of x equals arc cosecant of x, then the derivative of f of x is equal to. These are easy. If you know the first three, the bottom three are just their negatives. In other words, the derivative of an inverse cofunction is the negative of the derivative of the corresponding inverse function. So the derivative of arc cosine is the negative of the derivative of arc sine. So it's just negative 1 over the square root of 1 minus x squared. Same thing for arc cotangent. Its derivative is negative 1 over x squared plus 1. And the same thing for arc cosecant. Its derivative is negative 1 over x times the square root of x squared minus 1. So I would know the three, and in fact, in the history of trigonometry, the big three were not sine, cosine, and tangent. In the history of trigonometry, the big three were actually sine, tangent, and secant. And then their cofunctions came in later, and for whatever reason that I don't know at the top of my head, cosine bumped secant off the list of the big three, and it's become sine, cosine, and tangent. But really, the original big three were sine, tangent, and secant, and then their cofunctions came into play.